So when you get into Calc 2, you will see that there is a big focus on integration. You'll look at more techniques for integrating functions, and you'll also look at ways of applying integration in different contexts. So I thought that we'll end this class with one more integration technique, just so that we've kind of covered a lot of the algebraic tools that you'll need when you get to Calc 2. And so in this last section, we'll talk about integration with inverse trig functions. Now you've already done differentiation with inverse trig functions, and so a lot of the expressions that you're going to be working with and things like that will look a little bit familiar, but it's going to be important to follow a certain strategy, just given the wide variety of functions and expressions that we've been integrating so far. So in general, whenever you are taking an antiderivative or finding an integral, you want to be looking at things like the following. You want to be considering power rules. You want to be considering knowledge of derivatives. If you can't apply a power rule, or if your integrand does not look like a derivative that you've seen before, then maybe consider the possibility that your integrand is a composite function, and maybe you can do a u sub for the inner part of the composite function. Or as we saw back in section 5.7, it's possible that sometimes you would do a u substitution for the entire denominator, or it's possible that you would do a u sub for the terms involving natural log. If all of those things kind of don't work out for you, or if they're not available to you, then the only other thing to consider is really a u sub for an inverse trig derivative. And so these are a little bit trickier because there's a couple different substitutions that are going to be involved. And like I mentioned, you've seen a little bit of this in the past when we've seen things like, the derivative of y equals arcsine of x. And so when we did the derivative of y equals arcsine of x, we saw that it was 1 over the square root of 1 minus x squared. And so now we're basically going to be going the other way. We're going to be starting with 1 over the root of 1 minus x squared and getting back to arcsine of x. But we're going to do it in a very structured way. So let's jump down to these examples. And in the examples, you're going to notice that I am going to try to completely capture what we have on the left side of these equations that are in this box here. So I'm going to be, if I identify my question as an inverse trig problem, I'm going to be doing a u substitution, and I'm also going to be doing kind of an a substitution in a sense. So when I look at this in example 1, do you see that the power rule doesn't apply? Do you also see that this isn't a function that you're familiar with as a common derivative? And do you see that if you try to do a u sub for the inner part of this composite function, and you let your u equal 1 minus 4x squared, that your du would be a term involving x, and you don't have a term involving x in here, so that's not even a possibility. You also can't do a u sub for the entire denominator, and there are no terms involving natural log. And so that's where my thinking would go to, okay, well maybe it's one of these that you see in this box here. Maybe it's a derivative. This integrand is a derivative involving inverse trig somehow. And so as I think about the derivatives involving inverse trig, or these integrands that you see in this box, the one that this looks most like is this very first one. And so one of the things that I do to start this is I say, okay, well if this is in the form du over the root of a squared minus u squared, let's note what our u is. And you can see that if this is a squared minus u squared down here, if u squared is equal to 4x squared, then u would be equal to 2x. And if a squared is equal to 1, then a would be equal to 1. However, we are going to be turning this into exactly what you see here. So we're going to be turning this into terms of u and du. So that means we need to continue with the du mathematics that we did before. So that would be taking the derivative of this ux equation. So if u is equal to 2x, then du is equal to 2dx. And you don't have 2dx in this problem, but we can make that happen. We put 2 in there, and then a 1/2 in front. And then this problem becomes 1/2 integral. Notice the 2dx. The 2dx can be replaced by du. And then I have over the root of, now if my a is 1, then isn't this exactly the root of a squared minus u squared? And so I try to get, when I do these inverse trig antiderivatives, I try to get the integrand to look exactly like you see on the left side of in this box. And so this is going to equal 1/2 times, we have arc sine of u over a plus c. And so now I can plug in what my u is, I can plug in what my a is. And so my answer in this case will be 1/2 arc sine of the quantity 2x over 1, which is obviously just 2x, and then you would have plus c. So that is my answer for number 1. Okay, so let's go through this a few more times just so you can kind of get the handle on how to approach these. Again, in number 2, do you see that when you look at this, you can't do certain things like let u equal the whole denominator? Because if you did, if you said, oh, I think u is going to be 1 plus 9x squared, wouldn't your du involve x? But you don't have x in the numerator at all, so that's not a possibility. And so if some of those earlier strategies aren't going to work or aren't going to apply, then look at this and then try to match it up with one of your inverse trig. And I think in the case of number 2, it looks like it's going to match up with our second one. And so if it was matching up with our second one, then I would say, okay, well then my u would have to be equal to something that I can square to get 9x squared. Okay, well then u is going to be 3x. And then the du would be equal to 3dx. Now you don't have 3dx in there. You actually have 12dx in there. And so there's different ways of handling this, but I think what I might do is I might say, okay, well, if I wanted it to be 3dx, then wouldn't we have to divide 12 by 4? And if we're dividing by 4 inside the integrand, then that's the same thing as multiplying by 4 on the outside. Sometimes students will also take that 12 out in front and then just start off with a 1dx all over 1 plus 9x squared. And then if you let u equal 3x and your du is 3dx, you would multiply by 3 in the inside and divide by 3 in front. In either case, look what you're going to end up with in the front, 12 divided by 3 or 4. So if u is equal to 3x, du is equal to 3dx, we should also note what a is equal to. And again, it looks like we're lining up with the second equation here, so a squared would be 1, making a equal to 1. So this now gets converted into 4 times the integral of, we have 3dx all over 1 plus 3x squared. And this is in the form 4 times the definite integral of du all over a squared plus u squared. And according to our formula, I can just go straight off of that. It says this is going to be 4 times 1 over a arctan of u over a and then plus c. And so all you need to do to finish this example out is we just need to plug in for a and plug in for u. So the final answer here is just going to be 4 arctan of 3x plus c. That's it. That is our answer. And like always, you can take the derivative to check, but this is the process. And so you're doing a u substitution. You still have to worry about du also, and then we likewise have this a substitution also. Okay, let's take a look at some more examples on the back. Okay, number 3, we have the indefinite integral of 1 over x root of 16x squared minus 9. And so again, you could consider u substitutions and things like that, but those u substitutions aren't going to take you anywhere. And so this one actually lines up with a lot like what we saw on the front, where we had the integral of du over u root of u squared minus a squared was equal to, it was equal to 1 over a, it was 1 over a arcsecant of absolute value of u over a, and then plus c. So we're going to see if we can apply this here. So if what I have in the integrand is similar to this, then my u squared would be 16x squared, making my u equal to 4x. Now my du is going to be 4 dx, and we don't have 4 dx in the integrand. We have 1 dx in the integrand. So I need to multiply by 4, and then I also need to divide by 4. But I want you to notice something. Do you see how this u should be the same as the u that's being squared inside here? And so if we're saying that my u is 4x, then don't I really need a 4 in front of this x here? So when you get the du equals 4 dx and you put the 4 up top, and then you're thinking about multiplying by 1/4 in the front, I'm going to take that 1/4 from the front. I'm actually going to bring that to the inside also. And the reason is we wanted that to be a 4x also, so that we could take this quantity out and plop u in its place. So now this becomes the integral of, you can see we're going to have 4 dx up top, so that's du. And now we do have our u times the square root of u squared minus 3 squared. And so if my a squared is 9, then a would be 3. And so we have u squared minus a squared. And so by definition, this is going to be equal to 1 over a arcsecant of the absolute value of u over a, and then plus c. So the very last step is just to plug in for u and plug in for a. So we end up with 1/3 arcsecant of the absolute value of 4x over 3, and then plus c. So there is my answer to question 3. In the next video, what I'm going to do is I'll take a look at these other examples that involve some definite integrals, and we'll finish on an example that is a little bit more sophisticated algebraically. But check those out in the next video now.